But today I want to talk about my findings on the Collatz conjecture after working on it for some time now, several months, as some kind of amateur mathematician that's been doing it as a hobby. Essentially, someone told me that it was impossible, and obviously, like any person out there, I said, well, maybe I can be the one, right? So I want to share what I've been working on in secret because I think I found some things that would be kind of interesting to mathematicians out there. But first of all, I should say that I'm not a mathematician, and everything I'm about to say is probably going to be very crude to mathematicians out there, and I apologize for that in advance. But I do believe I found some really helpful things that I think can help us solve the Collatz conjecture. In truth, I'm probably doing this to just kind of think out loud because I've been working on it for so long, and I have a mess of notes, and I'm trying to clean it up and organize my thoughts. I'm going to do it publicly for everybody so you can laugh at me. So first, I'm going to assume that you're familiar with the Collatz conjecture. But let's start with how I've chosen to approach it. So first thing is uh, any odd number is going to be multiplied by 3 and added to by 1, and any even number be divided by 2. What I've noticed is that 3n plus 1 with any odd number results in an even number. So another way to kind of write this conjecture is an odd is going to be multiplied by 3, added to by 1, and divided by 2 some amount of time. Or an even number is always going to be divided by 2 some amount of times, right? Um, but now let's start with the number line. So when normal people look at the number line, they see 1, 2, 3, 4, 5, dot, 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 dot. Well, in this conjecture, chose to look at the number line in a different way. The way that I've chosen to look at it is the odd numbers, 1, 3, 5, 7, 9, etc. That's 4, 9, and their doubles. So 1 is what we already have. Its double is 2, and then we have 3. And then if we double 2 again, we get 4. So maybe I'll write it up here so it'll be easier to see. 4. Then we already have 5. 3's double, 6, 6, and so forth. So what I've chosen to say for this conjecture is you don't need to solve for every single number. You only need to solve for the odd numbers because the even numbers will be divided by 2 to arrive at the odd numbers. And then I can take that even one step further. If you take an odd number and multiply by 3, it is now an odd multiple of 3. But if you add by 1, it becomes an even number that is not a multiple of 3. Um, then you'll divide it by 2 some amount of times, and it still will not be an odd multiple of 3. It just can't be. Therefore, what I've concluded is that you may choose an odd multiple of 3 as a starting number. So s of 0 equals 3 to the n. But when you run the conjecture, multiply by 3, add 1, and divide by 2 some amount, you will never again arrive at an odd multiple of 3. Now, going through the conjecture in one step will never prove or disprove the conjecture because the only number that can start with itself and then become itself again is 1. And that can be proven. So we can ignore 1 as the exception. That's also to say that 1 isn't a multiple of 3 either. Um, so essentially, instead of choosing to look at all numbers or choosing to look at all odd numbers for the conjecture, I've only chosen to look at odd non-multiples of 3. So let me just write the odd numbers out real quick because I need to organize them in a very special way. So 1, 3, 5, 7, 9, 13, 15, 17. So the way of choosing to organize these odd numbers are what I call mod 1s, mod 0s, and mod 2s. So the mod 0s, again, we don't care about because if we can prove it for all odd non-multiples of 3, we can prove it for all numbers because the multiples of 3 become non-multiples of 3. That leaves us with the mod 1s and the mods 2s, which have very special characteristics to them, which I'll explain in a second. But first, I need to explain mod 1s and mod 2s for those who aren't familiar. So if you take 3 and divide it by 3, you have 0 remainder because it's completely divisible. 3 is completely divisible by 3. If you take 2 and divide it by 3, you have 0.6667, which another way to represent that is 0 with a remainder of 2. And if you do a 1 over 3, it is 1, I'm sorry, it's 0 plus a remainder of 1. And again, I'm not a mathematician, so I don't know how to formally write this, but I'm hoping that you get the point, even if you're Joe Schmo in the street who's never done math. Let me just do one more and make it clear. So you have 4 divided by 3. You will have 3 plus 1 over 4, essentially. I'm sorry, over 3. Oops, I did that wrong. I just cross it out. There we go. There we go. You have 1 plus 3 over 3. So 3 and 3 goes into each other one full time, but you have a remainder of 1. So you have 1 plus 1 remainder. So when you're looking at mods, you're only looking at the remainder numbers. So now let's go back to the columns that I've chosen over here. So if you have 1 and you divide it by 3, you have a remainder of 1. If you have 7 and you divide it by 3, you have a remainder of 1. Because 7 goes into 3 twice for 6. 7 minus 6 is 1 left over, mod 1. Okay, so that's how mod 1s and mod 2s are separated. Now, why I've chosen to separate them? Well, like I said before, they have special properties to them. So here I have this table that I've created where you have the two ADIC numbers and then every single number underneath it. So what is a two ADIC number? According to my research, and I don't know if it's correct or not, so you'll have to excuse me, is that if you take 1, 5, 21, 85, and run them in the conjecture, you're going to multiply them all by 3. So you get 3, oops, 3, 15, 63, and I don't know what that is, 255. And then you're going to add 1, so 4, 16, 64, and 256, and divide by 2. They're all going to arrive at the two ADIC number of 1. So what I'm really saying is all these numbers don't have to be proven, because if we can prove 1, we've proved all these numbers. So when we go back to the Excel sheet, every row represents what I call a series of numbers that, when given a conjecture, will equal the two ADIC number. I hope that makes sense. Now, each two ADIC number is either going to be a mod 1 or a mod 2 number, which I've highlighted in either red or blue respectively. So red is every mod 1 number, so 1, 7, 13, and blue is every mod 2 number, so 5, 11, 17, etc. Like I said before, they have special properties to them. Every number in the series of the two ADIC 1, when given the conjecture, is going to be divided by 2 an even amount of times. See how the column heading, which is the divisions of 2, is always even for the numbers underneath the series of 1. Now, every mod 2 number is going to be divided by 2 for every number in the series an odd amount of times, which you can separate into little columns like I've created in this chart right here, which I was trying to highlight, but I guess I can't, where we have the mod 2 numbers on the left and the mod 1 numbers on the right. Now, there are tons of observations you can make. Excuse me, I'm a little under the weather right now, but curiosity never stops for sickness. Why is that important? Well, the reason why it's important is because there's kind of two ways to kind of come at this conjecture. You can either say, all right, let me take any number and show you that it can approach 1 through the conjecture, or you can start at 1 and show that it grows into every single number. Either way can be used to prove or disprove the conjecture. It's just a matter of perspective, I'm assuming. But I've kind of chosen to look at it from the inverted perspective, as I would call it, that is kind of backwards. Essentially, instead of saying you're choosing any number, multiplying it by 3, added 2 by 1, divided by 2 some amount of times to arrive at 1, I'm saying you take 1, you multiply it by 2 any amount of times, you subtract 1 and divide it by 3 to arrive at all numbers. Okay, so the trick would be trying to find the A. What is the pattern of A's that we can get to arrive at one or arrive at any number? So it would be really, really cool if we could just say, all right, we start at one, and one is a mod one number, so it can go 2, 4, 6, 8, etc. But the problem with that is that there are mod zero numbers built into it. Okay, so when we look at the numbers in the series for one, which is row 2 here, you'll see that we have a mod one number, one, a mod two number 5, and a mod zero number 21. And the pattern continues where it goes red, blue, black, red, blue, black. 5 is a mod two number, and it goes mod 0 with 3, mod 1 of 13, mod 2 of 53, and then so forth. You'll notice that it always goes whatever number it starts at, but we'll just assume that it's mod 1. Mod 1, mod 2, mod 0, mod 1, mod 2, mod 0. It might start at mod 0, but the pattern will continue. Mod 0 goes to mod 1, mod 2, mod 0, and it continues. However, that's where I enter the mod 18 numbers. So you'll see that 1 through 17, sorry, 1 through 17, so these numbers right here, all exhibit the same pattern where they start with a mod 1, mod 2, mod 0. And if you go to 19, you have mod 1, mod 2, mod 0. If you go to 5, it goes mod 0, mod 1, mod 2. And if you go to 23, you go mod 0, mod 1, mod 2, etc., etc., etc. So there's only 18 possible combinations of these mod 18 numbers. Now, why is that important? Well, at first, I was hoping that I would be able to come up with an equation that's missing with the Collatz conjecture, which is, say, 1 is our starting point. This is where n equals 0. What if we can have a formula that says if n equals 1, what are the possible branches that we can, what are the possible numbers that can arrive from 1? Well, as you saw in our 1 series, for the 2-adic one, we can get 1, 5, 21, 85, 341, dot, 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 dot. So if we can come up with a formula that says at any n, so n equals whatever number you want, you can get every single number that exists. So if you want, say n is 3, and you want to come up with all the numbers that you get from 1, from 5, from 21, from 85, from 341, I feel like that would be massively important into trying to solve the conjecture. So that's kind of what I did in one approach, is I came up with these different formulas where n equals 1 is this formula, n equals 2 equals that formula, n equals 3 equals that formula. And we would need a function. The biggest portion of this kind of method would be trying to figure out the amount of divisions, or in this case, the multiplications of 2. So like I said before, we have 1, which can be multiplied by 2 an even amount of times, so 2, 4, and 6, etc. So we'll just do etc. So we want a function to be able to figure out, all right, so we start with this number, we figure out what mod 18 it is, and we can figure out what branch we get of possibilities. But we know that 2 to the power of 6, which is 21, and that might be confusing. Essentially, you start with 21, multiply by 3, add by 1, and divide by 2 to the power 6. This is my shorthand notation for what I'm saying. You arrive at 1. Is a multiple of 3. Therefore, there can't be branches off of 21. The conjecture can never start at some number, multiply by 3, add by 1, divided by 2, any amount of times to arrive at 21. It's just impossible. So 21 is kind of a stopping point. So we can't just say we're using the mod 3, so 1 mod 3, etc., to arrive at 2, 4, 8, 6, whatever. We need to use the mod 18s because the mod 18s show us what pattern of evens that are possible or odds that are possible, while also showing us the branches that can't exist. So I've created a formula for that. We'll go into Desmos real quick. We can see, all right, let's start with, I'm using, okay, let's start with 1. Okay, so 1 is going to be, uh, have numbers in the series when y is equal to 0. When numbers are multiplied by 2 amount of times, 2 to the power 2, I should say, or 2 to the power 4, or 8, or 10. And if we look at the Excel sheet, we'll see that 1 has numbers in the series where it's multiplied by 2 to the power 2, 4, not 6, but 8 and 10, and 14 and 16, etc. If we do my formula for 5, we should get 3, 5. We should get 3, 5, 9, 11, etc. So let's see if my formula works. Okay, so we get 3, 5, 9, 11, etc., etc., etc. So now let's plug in a bigger number, which is like 199. If you do 199 and you do mod 18 of it, you get 1. So in theory, 199 should not be any different than 1. And that is true. See, all the numbers that are included in the series for the 2adic 199 are numbers that are multiplied by 2 to the power 2, or 4, or 8, or 10, etc. Now, I was hoping that I could use my formula and say that if I had an equation just like this, that I would be able to use it to solve or prove or disprove the conjecture. But my formula is essentially, if we take the one from the Word document, 3n, any chosen number plus 1/3, arrive at 2 to the function that I've created. If we do this, I'm not entirely sure my formula works just by the practical use of it. Because my formula is essentially y equals some mess. It's a very large formula. I'll actually show you it right now. There it is. Everything in the green font. So 0 equals mod x minus x, whatever, etc. Y equals some s, where y is equal to 0. It might be that my formula can be used. It might be that you can do 3n c plus 1/3 2 to my formula. We'll say y, and then set y equal to 0. But I'm not entirely sure how to do that. So I almost have this gut feeling that it's impossible. So I've moved on from it, and I've decided that maybe there's a different way to approach it. If you know how to do it, that'd be very amazing to see. But I don't. So I'm going about it a different way, and this is where I'm trying to kind of talk to everybody about it and organize my thoughts out loud. Essentially, I've decided that, okay, well, one, we want to know the patterns of mod 18 numbers. So if you look at 1 in the 2adic 1 series and run it through the conjecture, you arrive at a mod 1 number. Well, I told you that 19 kind of repeats itself, right? Repeats 1, I should say. But 25 is not a mod 18 equals 1 number. 25 is a 25. If you take 25 and do mod of 18, you get 7, right? 7, yep. And essentially, I want to find the patterns of mod 18 numbers, because then I can find the possible branches off of 1, and the possible branches off of those numbers, and the possible branches off of those numbers, etc. Because I want to find the 1, 2, 3, 4, 5, the complete different paths that one can take to figure out all the numbers that it can create. And I've found some pretty interesting patterns. So the first one is that 1 and 19, yes, they both equal mod 1 numbers, but they don't equal the same mod 18 numbers. So this is a 1 and this is a 7. If you go another 18 down, so 37, you're going to get 49, which 49 mod 18, I believe off the top of my head is 13. 36, 13, yes, that's correct, is 13. But if you run it one more time to 55, you get a mod 1 number again. And if you do this again and again and again and again and again, the pattern repeats itself. What's cool though is that now you take this one and run it through the conjecture. You will get 1 for the first one, but 7 for the next one. Now, if you were to run this conjecture not to 55, but to 55 a third time, so 163. So say we go all the way down to 163, you will find that 163 is a mod 1 number, that when run through the conjecture is a mod 1 number, which run through the conjecture is a mod 7 number. So you build up mod 1 of 18. Well, I guess mod 8, x mod 18 equals 1, and you build it up. The same pattern exists when you go horizontally, not in the same way, but the same uh, idea anyway, where you have a mod 1 number here, but you don't have another mod 1 number until here, 2 to the power of 2 plus 18. And if I were to go 2 to the power of 2 plus 18 plus 18, you get another mod 1 number. It repeats every 18. And the same thing happens where if you run this to the conjecture, it becomes, I believe, 17, whereas 2 to the power of 2 becomes 1. And if you run it again, you get, if you get it to 2 to the power of 2 plus 18, and you get a mod 1. And if you run it to the conjecture, I believe you get mod 3. And if you do 2 to the power of 2 plus 18 plus 18 plus 18, you get 1, which becomes a 1. And if you run each to conjecture, you get 1, and then you get 17, and then 3, and then 1, and et cetera, et cetera, et cetera. So you see that there's definitely a pattern, and it definitely helps because you can find all the possible branches out of 1 and prove that no matter how many times you do it, you'll never arrive at a number that becomes itself kind of deal. In theory, that's what we'll be looking for. So that's the current stuff I'm on right now. If you look at my Word document that kind of collects all my work, you'll see that I've gone through and tried to figure out all the patterns of mod 18 numbers and how they branch and how they relate to each other. I'm not done yet, but that's kind of the process I'm going through right now to solve the conjecture. And I think it can be done. It's just a lot of tedious work. And it's just, I don't have a lot of time to do it. But that's where I'm at. And I think that this is very interesting for people because I think I've looked at some people after I've kind of done this and before I've done this video and found that everyone kind of arrived at the same thing, which is they didn't know. So they came up with some kind of formulas. So they might come up with like 1 always gets to 21 by taking 4n over 3 if it's an old number, or 2. I don't know. It's just, I think what people have been missing is that the mod numbers have specific properties to them. And that is how you figure out whether it's divided by 2 X amount of times. And I think that's important to figuring out the conjecture. You want to be able to know that a number is going to be multiplied by 3 and added to by 1 and divided by 2 an exact amount of times. You want to know the exact pattern of divisions by 2. That way you can arrive at 1. And that's what I'm trying to figure out is what are the exact patterns of divisions of 2? Or if you're doing it my way, what are the exact patterns of multiplications of 2 from 1? And that is my work. And I hope you enjoyed it. And if you have any questions, comments, whatever, feel free to leave them down below. I know it's a mess, and yeah, enjoy.